In this lecture, we are going to talk about unlimited point algorithm. It's also another way of dealing with inequality constraints in nonlinear optimization. So we want to adjust the Kkt conditions. Let's just write down the problem. Minimizing f of x subject to g of x is equal to 0. H of x is less than or equal to 0. We transform h of x to h of x plus z is 0. And z is greater than or equal to 0. So our Kkt conditions are going to look like this. First, write the Lagrange function f of x plus lambda transpose g of x plus mu transpose h of x plus z. All right, so our Kkt conditions are going to be derivative with respect to x, which is equal to 0. Derivative of Lagrange function with respect to lambda, which is equality constraint, 0. Derivative with respect to mu, which is h of x plus z is equal to 0. And we know that also h of x should be less than or equal to 0 because we don't have the barrier term here. We only have the original objective function. And then diagonal mu, derivative with respect to mu, which is going to be diagonal mu multiplied by h of x is equal to 0. Mu is greater than or equal to 0, and z is greater than or equal to. So here we also have minus diagonal mu z. All right, now what's our goal? We want to get rid of some of these constraints that we have here. What's the main one? Is this inequality constraint. How can we deal with this inequality constraint? And also, we want to remove this diagonal mu multiplied by h of x. So how can we do that? The idea for unlimited point algorithm is to make sure that, we also want to get rid of this one. So in order to do this, to make sure that z is unlimited, what we can do, we can use 2r, where r is a positive integer, or it's like a natural number, to make sure that no matter z is positive or negative, z to power 2r is going to be positive. For example, if r is equal to 1, you are going to have z squared. So if z is positive or negative, in any case, this value is going to be positive and it satisfies this constraint. It also is going to affect our Kkt conditions. So let me rewrite the problem again. So we are going to have minimizing f of x subject to g of x 0 and h of x plus z to power 2r is equal to 0. Here we don't have z should be greater than or equal to 0 anymore. So our Lagrange function is f of x plus lambda transpose g of x plus mu transpose. Actually, for mu's, we do the same thing to make sure our mu's are positive. So we also get rid of this constraint, which mu should be greater or equal to 0, h of x plus z to power 2r. So we have two changes, one for z, one for each of our mu's. So let's look at our Kkt conditions. First one, derivative with respect to x lambda plus derivative of inequality constraint transpose, and here we have mu, each of the mu's to power 2s. Get rid of the positivity constraints for mu. Then, with respect to lambda, which is our equality constraint, with respect to mu, so we have h of x plus z to power 2r is equal to 0, and then diagonal mu multiplied by derivative with respect to mu. This time, again, this is going to be simplified to diagonal mu to power 2s multiplied by z to power 2r. Going to be 0. And also, mu was positive before, z was positive. So now we don't have these two constraints anymore. So as you can see, we added these terms to ensure that z to power 2r and mu to power 2s are positive. We simplified or adjusted our Kkt conditions by doing so. So now we don't have any inequalities anymore. If you look at this, no inequality constraints anymore. So what we can do next is to simply apply Newton-Raphson. So we started with, let's go back to the previous slide. We started with the original function. Instead of adding a barrier term to the objective function, we added z, which is positive here, and we made sure that z is to power 2r to get rid of this constraint, which is z should be greater than or equal to 0. Then we wanted to get rid of h of x is less than or equal to 0. This is how we do that. We are going to do this for both mu's and z. So both mu and z are positive by using this power, these even powers, like mu to power 2s and z to power 2r. All right, let's write the step-by-step implementation of unlimited point algorithm. Step 1 is to reformulate our optimization problem. Step 2 is to initialize all of the values. So choose initial values for x0, all of our variables, our Lagrange multipliers, both for equality and inequality, and z0. 3, carry out 1 Newton-Raphson step for Kkt conditions. That only include equality constraints. So even if you have inequalities, inequality constraints, transform them into equality. All right. In the next step, use the update rule for Newton-Raphson to update the vectors x, lambda, mu, and z. The next step, check the termination criteria. for Newton-Raphson algorithm. So if the termination criteria is satisfied, if it's satisfied, it means the optimal solution found. Else, we go to step 6, increase the iteration counter and go to step 3. So this is step 3. So we do this iteratively. This is like iteratively until we reach convergence. So in this lecture, we talked about unlimited point algorithm. This is a new type of reformulation for minimizing f of x subject to g of x is equal to 0, h of x is less than or equal to 0. What was our reformulation? Minimizing f of x. We have x's here, we have z's here, subject to g of x is equal to 0, and h of x plus z to power 2r is equal to 0, where r can be any positive integer. But only one value for r would be sufficient. And then based on this, we write the Kkt conditions. In the Kkt conditions, again, instead of mu, which is corresponding Lagrange multiplier for this, we use mu to power 2s, so that we don't need this positivity constraint for mu anymore.